So the mass deflects off after hitting a rod at an angle theta, while the rod swings about a pivot point over here and swings up until at 90 degrees exactly, and that is the maximum height it goes. So we are asked to find
the angular velocity of the bar.
Okay. So it's
Okay. So first we have conservation of momentum. So we have I initial ow equals I final, which gives us Bill stop. 1/2 I times omega squared equals mgh. And h equals L over 2. Then we can plug that in. And the I of the swinging bar is ml squared over 3. So we have ml squared over 3 times omega squared. And then if we solve for omega, we eventually get, I'll skip the algebra, 3g over L. And if you plug it in, we should get a numerical value of 4.95 radians per second.
okay. That is it for part A. In part B, we are asked to find the velocity of the object right after the collision. So we use this. It is said in the problem that kinetic energy is conserved, so we will use conservation of energy. Note that the kinetic energy that the rod has immediately after the collision is equal to the gain in potential gravitational energy from when it is in this position to at its fullest height. And this would be its reference point. So we have the initial energy, which is 1/2 mv initial squared.
Which m is that?
Small m.
Okay.
Is equal to the final velocity, which is 1/2 mv final squared, plus mgh. What, this is big M. And h is L over 2. Solving this equation for V final, because we know everything else, we find that
Yeah. Okay.
so just solve for V final and you get this.
Great. Are we done?
Letter C. No. Now we need to do letter C.
Hot shit.
Okay. Part C, we're looking for the angular momentum of what angular momentum are we looking for? Of this ball. Okay, so angular momentum L equals moment of inertia times omega. And the moment of inertia of this particle is mr squared times omega of the object. Now omega also equals v over r, so we can plug that in. So we get mr squared times v over r. Our r's cancel out, and our angular momentum is mrv. And if we plug in our values, we get L equals 12 kilograms. Wait, Bill, what are the units for this? Meters per second.
Not meters per second, just per second. So there's no meters. Radians per second.
Kilogram? No, we're looking for angular momentum.
Yeah, kilogram radian per second.
Kilogram radians per second. Okay. You want to do letter D, Bill?
Okay. Let's do letter D. can't talk this. The mass deflexor.
The theta.
This theta thingy that is between these not so straight lines segments. So we know that the angular momentum is conserved. Because it says that in the problem. So we can use conservation of angular momentum, and from that we have
What are we solving for here, Bill?
we will be solving for theta. Note that theta is not in this equation, but what is in this equation is the x component of the final velocity, and that is in the final angular velocity of this small mass. So we will solve for that by, we know that the moment of inertia of this small ball thing is just ml squared. So ml squared, and this would just be v over l is equal to ml squared, the initial. This would be v x final over l again, plus the moment of inertia for the rod is 1/3 ml squared, and then the angular velocity of that, actually found in point A, is 4.95 meters per second. Solving for v sub x final, we get is equal to 4.06 meters per second. So we know that cos of theta is equal to v is equal to that. So theta is then just equal to the inverse of the cosine of, which is equal to cos -1 of 4.06 over 8.04, which is equal to approximately 59.3 degrees. And we have time.